Okay, so as promised, I'm going to do a little run through of a calculation of just an estimation of the quantities, the numbers and the fractions in the Drake equation, and see what number I come up with at the end. And then we'll talk about kind of where the biggest uncertainties are. And the biggest uncertainty, spoiler alert, is the last couple of terms. Hopefully you got a chance to watch the Carl Sagan video that I posted in the pages section to YouTube. So check that out if you haven't already, but let me try my hand at this. So first of all, I changed all my pens to match the color scheme. No, they're all invisible. So change all the colors to light colors. The first term in Drake equations, n sub star. N sub star is the number of stars in the Milky Way galaxy. And we can give a number for that anywhere between kind of 2 billion and 4 billion. In order to keep things rounded off, I'm just going to use 1 billion. Now, why only use 1 billion if the number of stars in the Milky Way is 2, 3, 4 billion? Sorry, 100 billion. Goodness. Let's start again. Okay, number of stars in the galaxy is 200 to 400 billion. I'm going to use 100 billion. That's 10 to the 11th. Why? Why not use 200 or 300 or 400? Well, one thing is because this kind of estimation problem, we're not worried about factors of 2, so we just round everything off. But the other thing is we want to count, we don't want to count O and B type stars for reasons that we'll talk about in the lecture that I'll do later today, because they're probably not habitable in any way. They probably can't have planetary systems for any significant amount of time. We don't want to count stars that are in triple star systems where it would be impossible for a planet to have a stable orbit. So I'm just going to round this one down to 100 billion. It's still a pretty big number. What fraction of stars have a planetary system associated with it? That number is looking pretty big. Kepler and TESS are finding planetary systems of some sort around most of the stars that they look at. So I'm tempted to use a number close to 100% for this. But let's be a little more reasonable with this number. And let's say it's definitely more than 50%. So if I'm trying to be conservative, I'll say 50%. So our running total is 0.5 times 10 to the 11th, a half times 100 billion, or 500 million, no, 50 million planetary systems in our galaxy. By the way, why are we only talking about our galaxy and not the whole universe? Because other galaxies are so far apart that it would take hundreds of millions or billions of years for even a radio signal to cross the space between the galaxies. So if there's life in other galaxies, we will never ever know about it. And it's not worth our time to even talk about it. We're talking about life within our own Milky Way. The next term in the Drake equation is how many, on average, Earth-like objects, in other words, potentially habitable. Maybe we should, to follow up from our lecture yesterday, instead of calling this n sub E, call this n sub H, the number of habitable, potentially habitable worlds in a typical solar system. Ours has 1. If our solar system is typical, then n sub H is 1. But maybe the number of potentially habitable places in our solar system is 4 or 5, right? Earth, maybe Mars a long time ago, Europa and Titan, maybe Enceladus or Ganymede. Let's say on average, there are 2 potentially habitable bodies in a typical solar system. This may be very optimistic. In fact, this is the same number I think that Carl Sagan chose. I try not to be influenced by this TV show that I watched 30 years ago, but 40 years ago, oh my goodness. But maybe I am influenced by it. Another reason to choose 2 is this 2 and this 50% cancel up, and we're back to 100 billion potentially habitable worlds in the Milky Way galaxy. I should use a different color for my running totals over here. The next term in the Drake equation is tricky. What fraction of potentially habitable planets or moons, potentially habitable bodies, on which the conditions are possibly suitable for life, does life actually, in fact, get started? I'm tempted to choose a number like 1% for this, only 1 out of every 100. That, I think, strikes a balance between optimism and pessimism. I think an optimist might say 10% or even 50%. That if you have the conditions for life, life will evolve. I'm not quite that optimistic. We also want to, well, I was going to say we want to roll out situations where life gets started and doesn't really go anywhere, but that's the next step, actually. So we don't want to roll those out yet. So I'm going to use 10%. Or 1% right now, which means my running total of number of planets or moons in our galaxy in which life has formed at some point in history is a billion. 1% of 100 billion is a billion. That's a pretty remarkably big number. It's a pretty remarkably big galaxy. The next term in the Drake equation is, given life, what fraction of inhabited planets, inhabited by some kind of life form, whether it's as simple as bacteria or single-celled organisms, on what fraction of planets does that evolve all the way up to what we would regard as intelligent life? And we said last time we can define intelligent any way we want. We have no guideline for this at all, other than the fact that life on Earth sat around for a pretty long time before anything interesting happened. A couple of billion years before we had anything other than single-celled organisms. If the sun was a A-type star, it would have gone supernova before the Cambrian explosion, before life colonized the land. So what do we choose for this number? I'm tempted to be a little more pessimistic about this number and choose 1 in 1,000. Okay, only 0.1%, given life, evolve into something that we might call intelligent life. That's considerably more pessimistic than Dr. Sagan's estimates if you watch that video. This brings us down to only 1 million. That is still a fairly remarkable number. 1 million intelligent beings, intelligent races of beings, on 1 million different worlds in our galaxy, if these estimates are even close to correct. The next, given intelligent life, and intelligent can mean as intelligent as a Homo habilis, or as intelligent as an octopus, or as intelligent as a dolphin, whatever you think intelligence means, what fraction of those make it all the way through fire and metallurgy and advanced society and discover electricity and can build radio telescopes or spaceships, things that we might come in contact with? Okay, either radio signals, interstellar, intergalactic communication, or actual spaceships going from one star to another. Again, we have nothing to go on here other than the fact that kind of from the time that humans learned how to use tools to now, where we're sending spaceships to Mars, was pretty fast in cosmic times, right? It was about 1.5 million years, maybe 2 million years. 2 million years out of the whole history of the planet is a really short time. So what do we want to choose for this number? I'm going to choose, I'm tempted to choose 1% again. Only 1 out of every 100. I think that's a little more pessimistic than I usually am. I think I choose the more optimistic 1 out of 10 sometimes when I do this. 1 out of 10 would give us 100,000, 10 to the 5th, intelligent civilizations in our galaxy. Okay? Kind of remarkable. Even if I choose 1%, that would still give us 10,000 intelligent civilizations in our galaxy. One might be tempted to say, well, where are they? How come we haven't come across any intelligent life forms outside of the Earth? Maybe if you watch a lot of flying saucer shows on the History Channel, you think we already have. I think that's very doubtful. Well, one reason might come from the next term in the Drake equation, which is the fraction of the lifespan of a star or planet that is occupied by such a civilization. Because the lifespan of a star is about 10 billion years. How long do we expect human civilization to last? Let's say human civilization lasts for 1 million years. That's a long time. Then this fraction, 1 million over 10 billion, that's 10 to the 6 over 10 to the 10th, is 10 to the minus 4, or 1/10,000th, which means this number is 10 and this number is 1. Uh-oh. Suddenly, a galaxy teeming with intelligent life starts to look like a galaxy that only has us in it. And this is where things get difficult to be optimistic. Because I don't know, what is this saying, by the way? This is saying that even if civilizations on average last for 1 million years, there is a very small chance that 2 of them will exist at the same time in the galaxy, because 1 million years is simply not that much time if you're talking about the 10 billion year lifespan of stars. So while there might have been thousands or tens of thousands of civilizations that emerged in the galaxy, there are never 2 in the galaxy at the same time, because they don't spend enough time being there. I just came up with a really silly and maybe kind of inappropriate analogy, but think about a restroom here on campus on a Friday. One of the restrooms on campus might get used hundreds of times a day, but because everybody who uses the restroom is only in there for 2 minutes, you might never see another person while you're in there, right? There's lots of people in and out of the restroom, but it's very rare that 2 people are in there at the same time. We can think of our galaxy that way. There are lots of civilizations that have their little time of existence in the Milky Way galaxy, but we always miss each other because we're only living for a few million years. Can we do better than this? Because this is kind of pathetic. Can we increase our optimism anywhere? Sure. If you watch Dr. Sagan's video, I think he uses something like 1/2 for this number and 1/2 for that number. Are these estimates based on anything? Not really. They're really based on whether you happen to be optimistic about the current state of the origin of life. What do we need to discover in order to say something about these numbers in here that is more than just an uneducated guess? What we would need to do is to actually discover life on Mars, life on Europa, life on Titan. That would convince us that, yeah, life is actually easy. Anytime you get the situations for life to happen, it happens. Maybe this is a 50-50 shot, okay? So the uncertainty is currently here, where the educated guesses start to become uneducated guesses. But we should not be too depressed by that, because when I was taking this course in college, the uncertainty was here. Right? We didn't know what fraction of stars had planets. We didn't know that Europa and Titan and Ganymede might potentially be habitable. So we are making progress. And like I said, the way to think of the Drake equation most productively is to think about it as a way to frame what questions we need to be able to answer. So am I personally optimistic or pessimistic about how much intelligent life might exist in our galaxy? I am personally optimistic. I would be surprised if we were the only intelligent life form in the whole galaxy. But when I go through the motions of the Drake equation, I never get a number that's more than 10 to 100 in the galaxy at any given time. And if there are only 100 intelligent civilizations in the galaxy, and the galaxy is 100,000 light years away, then the closest civilizations might be thousands of light years apart. That's not exactly a crowded galaxy. What we'll do on Thursday is we'll talk about, all right, let's suppose that galaxies are filled with life, but that life tends to be thousands of light years apart. Is there any chance that these life forms in the galaxy could either travel to one another or communicate with one another through some methods that would be detectable? The technical name for the search for extraterrestrial intelligence is sometimes referred to in the community as SETI, search for extraterrestrial intelligence. And we'll talk about whether anyone thinks this is a worthwhile thing to do, okay? Given that there could be a small handful of advanced civilizations in the galaxy. We'll talk about what some of the implications of that are. Okay, so don't take any of these numbers too seriously, rather take it as a way to frame the question and as a realization that if we hope to overlap with any other civilizations in our galaxy, we have to figure out a way to hang around the galaxy for millions of years. Because if we don't, if this number is just 1,000, or I guess it's already been 1,000, is only 10,000 years, okay, then this number becomes less than 1. We're the only ones here. And if that's typical, if it's typical for civilizations to only last 10,000 or 100,000 years, then there's nobody out there probably to talk to. So one side effect of the Drake equation is it forces you to think about how might we figure out how civilizations could last for hundreds of thousands or millions of years on a planet. Does it involve moving to other planets and colonizing them? Does it involve figuring out some way to stop using up the planet's resources? Does it involve figuring out some way not to blow each other up and do all the things that Carl Sagan was worried about were going to happen in the Cold War in the 80s? It involves all those things. So another thing that the Drake equation is a meditation on the very tiny amount of time we spend in the universe compared to the length of the life of a star or a galaxy. All right, so I'll go ahead and leave that there. I'll record another lecture later today about stars and habitability. And then on Thursday, I'll record a lecture about SETI and how to send a signal to an alien civilization and stuff like that.